All right, so it's 10 past 3 already, and we can start. You were saying that we have a phenomenon called aliasing. If the sampling frequency is not high enough to cover everything, all the frequencies inside a band-limited signal, so the signal must be band-limited, and it must contain a maximum frequency, and your sampling frequency must be over twice of that maximum frequency. That is the necessary condition to avoid aliasing. And if that aliasing is avoided, it is called the Nyquist condition. By the way, the Nyquist frequency is the, if somebody asks you a question, what is the Nyquist frequency? Nyquist frequency is half of the sampling frequency, okay? That is the Nyquist frequency. And half of that must be, half of the sampling frequency must be more than the maximum frequency that you may have. Only then, with those replicas, we can apply a low-pass filter and isolate a replica around the DC of zero frequency. However, that's an unfortunate situation. Although this is the technically correct way of attacking this problem, knowledge of this is everything that you need to know. It's all you have to know about sampling. There's this Nyquist frequency, and your maximum frequency inside the signal must be less than that. Or if you have a maximum frequency of your signal, then your sampling frequency must be more than twice of that maximum. Unfortunately, in exam questions, the professors just love to ask tricky and puzzle questions to fool you. Because under some certain cases, it's not only the low-pass filter that we apply. If your signal is not low-pass band-limited, but if it is band-pass band-limited, even after making so many replicas, those narrow band regions may not overlap with one another, so they can be isolated, and the original continuous time signal can be reconstructed. But that isolation procedure will not be the ideal low-pass filtering with a cutoff frequency of omega s over 2. That will be something else. The reconstruction, digital to analog conversion filter will also be a band-limited band-pass filter in that case, and we'll just love asking such questions. But it's unfortunate, as I say, because in real life, those are never encountered. Those are just questions that are artificially fabricated to make you guys, the students, to make mistakes in answering exam questions. We love doing those things. So let me give, before the sampling of a sinusoid, let me show you some example. Let me try to fabricate those tricky questions, an example of those tricky questions. For instance, suppose that your signal is 10, 20, 30, 40, and 50, okay? It is band limited, it's a band pass signal. So this is 0, 10, 20, 30, 40, and 50. This axis could be radians per second or could be hertz, 1/2. Just whatever it is, okay? It's a frequency axis. If the axis is F, then you give the answer in terms of hertz for sampling frequencies. If it is notated as omega, it would be radians per second that you have to give the label. We're not interested in those things. This could be F or omega, whatever it is. But these are the labels, okay? Between 40 and 50, let's say hertz, there is a signal, and similarly, since it's corresponding to a real signal, we also have its conjugate parts here. It's not really flat, but I'm trying to emphasize that the signal is contained between 40 and 50 hertz and minus 40 and minus 50 hertz, like this. So a question that we love to ask, okay, I'm giving you already a hint or a cheating for an exam question that you will most definitely encounter right now, because while preparing my exam questions, I just draw such things, and I say, it's okay, so let me ask this. So that's what I'm doing now. The question of interest is, what is the Nyquist frequency? The question may contain two parts. Part A, what is the Nyquist frequency? The Nyquist frequency is the maximum frequency that is appearing inside this signal. So this is x of j omega. And the Nyquist frequency, the answer to this is 50, let's say hertz. So the normal way of attacking this problem is to say that, therefore, the minimum sampling rate, rate or frequency and rate mean the same thing. They're just they just correspond to the same thing. The minimum sampling frequency is twice of this 50 hertz, which is 100 hertz. And in fact, if you choose the sampling frequency to be 100 hertz, it will appear like this: 60, 70, 80, 90. 100 is here, and around this 100, 10, 20, 30, 40, 50, let's say, around this, the replica of these two band-limited portions will appear like this. It's the first replica around 100. Of course, at multiples of that, there will be other replicas. Around 200, there will be another extra, which will probably look like this. And some other replicas from the left-hand side. Yes. Do not forget to repeat everything, both on the right-hand side and at the left-hand side, because we are convolving this spectrum with an impulse strain. So as you see, there is no overlap. Therefore, aliasing is avoided. But as I said before, since we love fooling you, at part B of the question, we ask this: what is the actual minimum sampling rate which avoids aliasing? This is part B of the question. And usually this is the place where students may fail. Because as you see, we have actually only these only this one, and this one will repeat itself to the right hand side and to the left hand side, and at some certain positions of repetitions, in fact there will be no overlap. It is possible to avoid overlap, but you have to be careful. It may be one to the right, it doesn't overlap, but two to the right and one to the left, they may start overlapping. So you have to be careful about making infinitely many replicas of these two rectangular blocks here that are centered around the origin and appearing at 40 to 50 hertz. So you switch them to the right by some amount. And you may see that actually they don't overlap. For instance, I'm not giving you an answer here. I'm not giving you a proper answer here because I don't want to. I want you to work on it if it is really that way, or if you can find even some smaller sampling frequency. Suppose that we choose a sampling frequency of 60 hertz. Okay, so sampling frequency is 60 hertz here. This is the center. If I choose this one to be the center, I may go to the left and to the right by 1, 2, 3, 4. It's here. And 1, 2, 3, 4 to 5 here. So these dotted two samples, they seem to not overlap with it, but I have to look at the other multiples as well. None of them should be overlapping. So 60 is the first repetition. Where is the second and maybe the third repetition? Where are they? The second repetition is at 120 if 60 is the sampling frequency. So around 120, let me go 1, 2, 3, 4 to the left, and 1, 2, 3, 4 to the right. So it will be like this. Okay, it seems not overlapping, which is a good news, but let's see what's happening at the negative parts. If this is 60, let me draw in a different color. 1, 2, 3, 4 to the right, and 4 to the left of that 60. So as far as I can see, things are going pretty well. Why is it pretty well? Because they don't overlap. But of course, now the reconstruction filter cutoff bandwidth is not 60 over 2, which is 30. Normally, omega s over 2, as we know. Omega s over 2 is the reconstruction bandwidth, right? So if you choose omega s to be equal to 60, then you choose 30 to be the reconstruction bandwidth. But will it work? So let me try this. If you have this low pass filter, which is at a cutoff frequency of 30 hertz, it seems to be reconstructing something, right? Two bars like that, but that signal is definitely not the signal that we are looking for. So it's not a low pass filter to reconstruct this kind of a sampling. This kind of sampling is okay, it's fine. There's no problem about aliasing, but how do we go back to the continuous time? It's certainly not this low pass filter that you see on the screen, because it reconstructs something else, something undesired. Instead, you need to design. That's a design process now to make the reconstruction. But I can see that, for example, from somewhere around here to somewhere around here as a bandpass filter, both for the positive and the negative frequencies. If I apply these, oops, it's not like that. Yeah, this is better. If I have these two bandpass filters, I can use them for reconstruction. And the answer to part B, what's the actual minimum sampling rate? One of the candidates that I can think of is actually 60 hertz. I'm sorry. But is it really the minimum? Can I find something even smaller than that one? And as you see, it is less than the Nyquist rates twice, which is 100 hertz, 60 hertz, not 6 hertz, of course. 60 hertz is definitely less than 100 hertz, and it seems to be pretty much okay. Can you find something smaller than this one, maybe 50 hertz? Just try it, but be careful. It must be overlapping nowhere with no multiples. How about 40 hertz? Looks kind of okay, because if I make replicas of 10 hertz shifts, it seems to be not overlapping, but only up to a point. After some point, that 10 hertz starts overlapping, maybe. Okay, you have to test it very accurately. So I'm not sure that 10 hertz will do the trick, but there may be some other frequencies where actually after infinitely many replicas, all those convolutions with respect to the impulse train convolutions, there will be no overlapping maybe. I found one of them, 60 hertz seems perfectly fine, but I don't guarantee that it's the minimum, and it may not be the minimum. So what is the minimum, right? This is a tricky question, and such a question is really not very much encountered in real life, and people just don't work that way. We just say that if you have a maximum frequency of something, then twice of it will correspond to the minimum sampling rate. For example, for the sampling of human speech, as I'm talking, the system here of the webinar is the computer is sampling my speech and making some other compression techniques, etc., transmitting that. But while sampling, if it is high fidelity sampling, then it must be, the sampling rate must be more than twice of what I can produce or what you can hear. And the human hearing system, ear system, is theoretically capable of hearing all the frequencies up to 20 kilohertz. Actually, it's not that far away. Only when you were a baby, you could hear until 20 hertz. But as you grow older, when you're a teenager, it reduces down to 18 kilohertz or something. As you grow older, it will reduce to 16 kilohertz. If you are very old, it may be 14 or 10 kilohertz even. But 20 kilohertz is the highest possible, let's say. So the standard high fidelity audio sampling rate is more than twice of that 20 kilohertz, which is more than 40 kilohertz. And in hi-fi audio, they use 44.1 kilohertz sampling, which is greater than twice of 20 kilohertz, which is the maximum hearable thing. But the digital to analog converters first apply a low-pass filter at a cutoff frequency of 20 kilohertz, and then makes this sampling. If you start sampling the speech that is coming from the microphone automatically at 44.1 kilohertz, there may still be some aliasing, because even if your ear cannot hear them, actually in the environment, such high frequency audio-like, supersonic a little bit, signals may exist. You must first cut off those things as audio processing people. And after that, you do the sampling, because you cannot hear doesn't mean that the signal is there. It can be there, so you must apply a band limiting anti-aliasing filter first. So this is what can be asked, okay? Such a question. I usually ask such questions. So be careful about that. Now, let's continue with an example of sampling a sinusoid. Because this sampling a sinusoid will be a very good example about what the aliasing really looks like. And trust me, you can find a lot of such examples on the internet as illustrations. I'm trying to draw all these things on the whiteboard, but if you search for aliasing sampling as keywords, you will find a lot of material regarding these things. So x of t is equal to cosine omega 0 t is the sinusoid with a single frequency. It has the maximum and the minimum. It's a very narrow bandwidth, but it's there. The frequency is omega 0. So we are sampling a signal whose Fourier transform x of j omega is essentially like this. Two impulses at omega 0 and minus omega 0. And from Fourier series coefficients, we know that the Fourier series coefficients from the Euler's expansion, they are 1 over 2 and 1 over 2. So when you multiply them with 2 pi, they will become pi and pi, like this, on the frequency axis. Now, a sampling frequency, omega s, somewhere around here, will make the replica, the first replica, to appear like this, at around omega s. Here it is omega s minus omega 0. Here it is omega s plus omega 0 with the same magnitudes of pi and pi. The convolution, I'm convoluting with an impulse train. Of course, after the convolution, it is reduced in magnitude by 1 over capital T, but let's do not take into account what's happening to the magnitudes. If the impulse is there, after the reconstruction, you always have a volume pot in your amplifiers, in your radios or whatever, audio system. You can always increase the volume. So the magnitude, I don't care about the magnitude right now, but the impulses must be there. And the others, oops, excuse me, what's happening? Sorry. And the other replicas are here and here, and here and here, etc. To the left and to the right. This is the ideal way of sampling. But suppose that we choose omega s. So let me continue as an additional example. Omega s is less than 2 omega 0. If that is the case, I will try to draw it here. And the situation becomes like this. We have these two impulses at omega 0 and minus omega 0. And omega s is somewhere here, which, as you see, is less than twice of omega 0, this point. So around that, I put two impulses, which will now be inside the first impulse. Because as you see, this size and this size, they are all omega 0 and omega 0. And this is omega s here. And clearly, there will be another replica from the left-hand side, like this and this. And of course, there will be other replicas like this and this. So the situation is a little bit awkward, as you can see. Something bad is happening here. If you focus to here, this is omega s. This point is omega s. And half of it, half of that omega s is here. And I'm going to put a low-pass filter at omega s over 2, as if I was doing something correct. At omega s over 2, I do a low-pass filter. This is a low-pass filter at omega s over 2, cutoff frequency. Now, my original frequency of my sinusoid was omega 0. Now, the new frequency is not omega 0 anymore. It will be what? It will be omega s minus omega 0, which is less than omega 0, by the way. So when I reconstruct these two impulses with this low-pass filter, I will still reconstruct a cosine, another cosine, but the new cosine, x reconstructed of t, will be cosine omega s minus omega 0 times t. It will not be cosine omega 0 t anymore. It will be this, cosine omega s minus omega 0 t, which is another sinusoid. So what's happening? A very odd situation happens when omega s is exactly equal to omega 0. Something very odd happens then, because this omega s minus omega 0 will be equal to 0 because omega s is equal to 0. So everything will be cosine 0, which is 1. That is a constant. So I sampled a cosine with a sampling rate that is exactly equal to the frequency. The sampling frequency is exactly the same as the frequency of the sinusoid, and I obtained a constant thing. That is the extreme aliasing that you can have. So this is a sinusoid that we have. Sorry for the bad illustration. I'm waiting for the illustration to arrive. I hope you're still hearing me. Yeah, it arrived. So the sampling period, therefore, the TS is exactly the same as the signal period, TX, which means that I'm sampling from here, and then from here, and then from here, and then from here, for instance, from here and from here, like this, which is, as you see, all constants. However, if I choose the sampling frequency or sampling period to be half of the signal period, which means sampling frequency is twice the signal frequency, then which was omega 0, twice omega 0, then it would be like this. Then the sampling period will be half of it. So I will choose these blacks as well as these. Okay, like this. Then with those ups and downs, all of them, now it is reproducible. I can interpolate between those up and down things, and I can reproduce the signal. If I even reduce the sampling period less than this one, which means I'm increasing the sampling frequency more than twice of omega 0, it will be even better with a more finely detailed sampling. But if it is less than the periods, this kind of a weird phenomenon comes into the picture. I think I should be showing you, yeah, here it is. I found an example from a web page. It was just an arbitrary web page that I clicked by typing sampling aliasing example on Google, and this came. Now, the pink, let me wait till it arrives, because it's not, it didn't arrive. Can you hear me now? Because, yeah, the figures are arriving a little bit late, unfortunately. I hope you're listening to me. Here in this sinusoidal shape, the pink continuous waveform is the continuous time signal. And inside it, there are some dots. Those dots are the sampling points. And those sampling points, as you see, if you choose the separation between those pulses, which is the sampling period, if you choose them smaller and smaller, which means larger and larger sampling frequency, you can sample the sinusoid like these small pink dots over there on it, which will be reproduced by simple interpolations quite accurately like this using a digital to analog conversion, which is a low pass filter technique as I indicated before. But if you choose the sampling period to be large, larger than or the sampling frequency to be smaller than twice of the maximum frequency or the frequency of the sinusoid, then those square, larger blue points would correspond to the sampling points. And if you interpolate those sampling points, as you see, you come up with still a sinusoid, but it will be a different sinusoid. The frequency of this sinusoid, this particular sinusoid, is omega s minus omega 0. Okay, it's a different frequency. It is a sinusoid, but it has nothing to do with the signal, which is a high frequency signal at the background that we try to sample. This phenomenon is a very good example of aliasing. And if you pick the sampling period to be exactly the same as the period of the signal, then it would stay constant. That constant effect in image processing or in video processing is also sometimes encountered. So in watching films, for example, the films are shown at, I don't know, 25 frames per second or something like that. 30 frames per second, let's say, okay? So at 1/30-second intervals, a new frame comes into the movie and you watch them. That is how you interpret a video. Suppose that you are watching a wheel that is rotating, or the wheel of a car, for instance, or a rotating wing propeller of an airplane. It's rotating. If by coincidence the rotation frequency of that rotating thing is also 30 hertz, that is 30 times rotating within a second, when you watch it with this sampling, this kind of sampling, you will see that rotating wheel to be stopping. So the car is moving, but the wheel does not rotate. It does not move. It's like it's staying constant, but the car is moving. That's a very odd and interesting thing to observe. And even more than that, if you go even below the frequency of that rotation, for example, if the wheel rotation is 50 hertz, but you are sampling at even less than that, 30 hertz, for example, 30 frames per second, then you see the rotation of the wheel in the backwards rotation. So the phase becomes negative in that case, and it looks like although the car is moving to the right, the wheel is rotating like this while the car is moving to the right. That's even a worse situation to observe. Nowadays, the movies are trying to avoid, they are avoiding these cases by temporal, time-wise filtering the video. So the video also has anti-aliasing filters so that these effects will not be visible. Instead, you see a blur as if it's moving, but you don't see it to be exactly staying constant or rotating backwards. It's just blurring those things, which is a good thing, by the way. In the old movies, old Western movies, for example, cowboy movies of Hollywood, they didn't do that. Of course, in the old times, they didn't have the technology to make those digital filterings. So they didn't filter it, but they were showing it. And when you watch those films, you can see some of the wheels to stay constant or rotate backwards, etc. That's an effect. So that is aliasing, okay, in short. All right, let's come back. Now at this point, the last thing for today is conversion of these samples to discrete time signals. Because what we found is not x of n. X of n is not there. What we find, for example, with these impulses on the frequency axis is still x sub p of j omega. We didn't have the Fourier transform of x of n, which is capital X of e to the j omega, right? That's a different story. So this is not discrete time Fourier transform. This is still continuous time Fourier transform, but there are impulses. So how do we convert those impulses into discrete time samples? The situation is essentially quite easy. Let me illustrate it from here. Let's call this the discrete time signal, which has the discrete time Fourier transform of capital X sub d of e to the j omega, okay? What we did was starting with the continuous time signal. The continuous time signal was, let's say, x sub c of t, okay? X sub c, meaning continuous time. And its Fourier transform was like this. This is just an illustration. Don't even assume that all the signals will be triangular like this. X sub c of j omega. This is the Fourier transform between minus omega c and omega c on the frequency axis. And then we sample it to come up with x sub p of j omega, which is the repetitions of these impulses. Fine. So let me illustrate them. I'm trying to find the relation in the Fourier domain, of course. In the time domain, the relation is obvious. It's just the samples. But what's happening on the frequency axis? This is xp of j omega. If this is 1, this is 1 over capital T, to be precise. This is omega s, which is equal to 2 pi over capital T. If the sampling period is capital T, the sampling frequency is omega s. And this is omega c, this is minus omega c. Now, from here, it's very easy to draw the Fourier transform of x of n. We just need to apply the property of the discrete time Fourier transform, which I had been repeating like tens or hundreds of times. What was the property of a discrete time Fourier transform? So I'm going to write xd of e to the j omega. Just by looking at xp of j omega, the one at the top, I will draw something. But that something that I draw must obey one rule. What was the rule for a discrete time Fourier transform? I'm expecting an answer from you now. You can say it, or you can write. Saying would be easier. 2 pi periodic, Salih Can. Thank you. Yes, because I had been repeating it all the time, right? It must be 2 pi periodic. So let's make it 2 pi periodic. And can we do it? Yes, we can. Fortunately or luckily, we can, because this is xp of j omega is also periodic. But what is the period? It's periodic with sorry, excuse me. It's periodic with omega s. Because as you see, it repeats itself at omega s, at 2 omega s, at 3 omega s, at minus omega s. So whenever I have an omega s, it's repeating itself. So it is periodic. So why don't we just make xp of j omega as if it is 2 pi periodic? What is the thing that we have to do to make it 2 pi periodic? It was previously periodic with omega s. Omega is 2 pi over capital T. So why don't I, so let me put it thinking here. Why don't I just multiply omega by capital T? If I multiply the axis of xp of j omega, the omega axis, by capital T, omega s becomes 2 pi, because omega s is 2 pi over capital T. times capital T will be 2 pi. And everything will be not periodic with omega s anymore. It will be periodic with 2 pi. So let me do it. What I'm doing is scale by capital T. I'm scaling the horizontal axis by capital T. It depends on the value of capital T, but if you just try to visualize it, and let's say capital T is close to 1, which is of course not correct, it will be something like maybe, I don't know, this. Of course, it must be scaled proportionally. I'm sorry if I cannot do that. You can even draw exactly the same as xp of j omega, the same figure downwards, and then say that this point is 2 pi, and this point is 0. The peak, let's not change the peak, because 2 pi is capital T times omega s, okay? This is 4 pi, which is capital T times 2 omega s, okay? And this is minus 2 pi. Something like this happens. Clearly, this point changes. This is not omega c anymore. It is capital T times omega c, unfortunately, because I have scaled the whole frequency axis, so it's not at omega c anymore, that cutoff frequency of the original continuous time signal. It is capital T times omega c. And this is the Fourier, it's the discrete time Fourier transform, of course. Discrete time Fourier transform of x of n. This is what is happening in the Fourier domain, if you think of it as the discrete time signal. Okay, so it's simple. So overall, from top to bottom, what is the sampling phenomenon then? You start with the Fourier transform. Let me wait until the screen responds, because it didn't respond. There it is. We start with the triangle, like the low pass, the baseband signal, which we want to sample. It must be a band limited signal. And we multiply with an impulse train. So we convolve in the Fourier transform with another impulse train, which means we are making replicas of those triangles as an auxiliary step, this step here, as an intermediate step, imaginary. Of course, it's not happening, but in terms of understanding what's going on in the Fourier domain, let's think of it. And then we have to scale the horizontal axis, the frequency axis of the sampled signal, to make it 2 pi periodic, and that we do it by multiplying the frequency scale, the frequency axis, by scaling with capital T. We multiply the omega axis by capital T, make it 2 pi periodic, and we come up with the eventual shape, which corresponds to the discrete time Fourier transform of x of n, x sub d of n, of course. So this is the situation that we have. And you have to be careful about this aliasing business. So when sampling, they mustn't overlap one another. If you choose the Nyquist, if you obey the Nyquist frequency for sampling, then you will definitely not have any sort of aliasing. But there may be bandpass signals where you can reduce the sampling rate a little bit more than that. You can have smaller sampling frequencies, in other words, which is also possible in terms of questions. But otherwise, this is the situation that we come up with. Now, I will stop at this point, but I want to indicate what I will do starting with the next week, at the beginning of the next week, a few minutes, but we don't have the time to do that. There's a process called discrete time processing of continuous time signals. because that's an engineering thing that we have to do. We have a continuous time signal. For example, the microphone is receiving our audio signal. There's a question, so let me first read it. Sampling rate frequency her zaman olabildiğince yüksek ne almalıyız uygulamalar? So let me translate to English for the completeness of the recording. Should we choose the sampling frequency as high as possible in our applications? The answer to this is yes and no. Yes, to be on the safe side. Then, of course, your sampling will be very much accurate and your processing will be accurate. But you must also think of it like this. What are you going to do with those samples? If your sampling frequency is too high, for a short duration of sampling, within a few seconds or a few minutes, you will have tremendously high amount of volume of data. So how are you going to store it? Or how are you going to transmit or send it to the cloud or to some other person through telecommunications? Then you are increasing your data. You don't really want to increase your data for telecommunication purposes because bandwidth is a problem and it takes too long to transmit and it takes a lot of hard disk to store, to save the file. So you don't really want that. You want to have as minimum number of samples as possible. For true genius of an engineer, you should in fact choose the minimum sampling rate. And you want to make the sampling frequency as small as possible or the sampling period as large as possible to gather as few samples as possible, as long as those samples are still reconstructible without any loss. As long as that is possible, you are trying to, in fact, reduce the sampling rate in most of the applications because hard disk is not cheap, bandwidth is not cheap, so you don't want that actually. True engineers must reduce the sampling frequency in many cases. So what I was telling you before this question was, how do we process? So we have a continuous time data coming in, and we are in real time sampling, converting to discrete time, and we have a discrete time input streaming coming into our computer. In our computer, we can apply a discrete time filter because computers can do that, or hardware, digital hardware can do that. We process the discrete time signal, and we output a discrete time output signal, y of n, let's say. So x of t was the input, x of n is the thing that arrives. We make it y of n, and y of n is now converted to y of t using the low-pass filter, the digital to analog converter. From here to here, from the input to the output, how can we notate or write the expression of the system that I originally did in discrete time? Or in continuous time, I want to have, for example, a low-pass filter. Can I do low-pass filtering using discrete time filters in my computer? But the overall effect will be the continuous time low-pass filtering of x of t, and y of t will be the output, the low-pass filtered version of x of t. Why am I doing this? Because computers are cheap. Analog electronics is an expensive thing. We don't really want to do continuous time filtering with real analog equipment. They are a little bit more expensive than computers nowadays, and they will become more and more expensive, and computers will be more and more cheaper. So you have the computer. With computer, you want to do continuous time filtering. How are you going to do that? What is the equivalent processes that relates the continuous time filter, low-pass filters, let's say, to the discrete time process that you are doing? What is the Fourier relation between these two is the thing that we will see next. And it's a critical thing, of course, because engineers will need to do it that way. We have computers. We're always doing discrete time or digital processing. But we want to process, meanwhile, continuous time signals, because in real life, the signals are continuous time. So this will be our next topic to handle. And that will be about the end of it. The digital to analog converter, the details will also be provided. I said in the frequency domain, it's a low pass filter, but it's a rectangular low pass filter. And if you think of it in the time domain, what's the inverse Fourier transform of a rectangular shape? It's a sink. So the impulse response is a sink, but sink is not causal because it's extending to the left and right. So we can never apply an ideal low pass filter in real life because it's not causal. So what are we gonna do? How can we approximate those things? We will also talk about those a little bit, and that will cover the sampling topic. So right now I can stop. Your friend had a question and we covered it. If you have any other questions, you can ask now. I'm giving you a few seconds. Otherwise, I will stop the recording and end the meeting, and we will meet next week. All right. So I don't see any questions arriving. So let's stop the recording, let's end the meeting, and see you next week at the same place, same hour. All right. Goodbye.